right now. So the question is, how do we know when to do this? And should we just change one variable or both, right? Well, log-log transformations are usually when you do transformations on both. That's why log is said twice, right? Log x and log y. So log-log transformations are often useful for data modeled by this basic formula. So y equals ax to the b power. So when x is raised to some constant's power, you often want to do a log-log transformation. It's just a nice rule of thumb. And when you do a log-log transformation, you're basically shrinking and expanding variables on both axes, right? So you're not just stretching out one or shrinking one variable. You're doing that to both, right? And so just to give you some ideas for how to do this, so I'm always going to put x here and y here. This is a case where all these variables, all these y's are sort of here they're squished together, but here they're not rising very quickly. So here the y's aren't rising very quickly, and then the y's rise very, very quickly, right? So the y's are all they're shooting up for each x, right? So here we would want to shrink y and expand x. And so when you see curves that are approximately this shape, you want to think, I want to shrink y and expand x. Here we have a slightly different situation where now we still want to shrink y because y is descending too quickly now, right? Y is descending very, very quickly here. But we also want to shrink x now here when the curve sort of goes like this, right? And I sort of think of it as you're almost keeping track of a circle that goes around like this, right? So that's the order that I've written it in. So here's 1, 2, 3, 4. So here's, in 1, you want to shrink y and expand x. In 2, you want to shrink y, but you also want to shrink x, right? X is also expanding too quickly. And here, we want to expand y, but shrink x. So here, y is it's not changing very fast up here. It's changing very, very little. So we want to sort of expand that out. But we want to shrink x because x is going up too quickly in relation to y. And here, for the last one, number 4, we want to expand y, but we also want to expand x. Because this curve, if you note, your y is changing in a way where it would be helpful to see it expanded outwards, because here it's going down very fast. And also with x, it would be helpful to expand x out because all the x's are squished up here, but sort of spread out there. So these are just nice rules of thumb. Obviously, you don't have to memorize these. Sometimes what I do is I play around with it a little bit. I try, shrinking one, expanding the other, as long as I can identify that these are all y equals ax to the b power sort of patterns. But if x is your exponent, right? So before it was y equals ax to the power b, right? But now this is ab to the power x, right? So here you probably just want to transform one variable and leave the other one alone. If you don't have if you're not able to sort of eyeball which one to do, try things out. There's no harm in playing around with it. But eventually, when you do decide on a transform, you want to have reasons for it instead of just it just seems like the right thing to do. All right, so now let's start with example 1. Create a set of data with this function, graph this data set, and what kind of transformation should be done to make this data more linear. Well, already we could see from this that this is an example of y equals ax to the b power, right? So that's a case where we're going to need to do a log-log transformation. We're going to need to do transformations to both x and y. But let's first look at the shape of it to see what, this data looks like. Okay. So if you download the examples, let's put in, it has, for example 1, I've already put in the function y equals a x to the power b. Let's put in a, which is 10, and b, negative 0.4. 10 and negative 0.4. Now, I've already seeded this with just a whole bunch of positive integers for x that are just steadily going up, all the way up to 33. So now let's find the corresponding y values. So in order to find y, we just have to follow this formula up here. So y equals a times x to the power b. And remember, Excel knows order of operations, so it should do the power before it does the multiplication. And once we have that, I'm just going to drag all this all the way down and get a whole set of data. I think I forgot to lock down, yes I did. So I forgot to lock down A and B, so that's why it's giving me all this craziness. So let's lock down A and lock down B. So once we have that, then I can. All right. And now we see we have this nice curve. If you remember, this is sort of like the second type of curve or so. So we know we need to do both kinds of transformations already, right? And it would be helpful for us if we could actually sort of shrink y, but also maybe shrink x. And log is a way of shrinking both of them. And so why don't we try log? So let's do log transform. So get log of x and get log of y. Feel free to also use natural log. I'm going to assume log base 10. And Excel thankfully has log, and I'm going to use log 10. And I'm going to put in my x, right? And so it's going to change x from this into the sort of exponent. So 10 to the 0 power will give us 1, right? And I'm going to do the same thing to y. Oops. Okay, so 10 to the first power, 1, to the power 1 will give us 10, right? And so I'm going to take that and copy and paste that all the way down and get a nice log transform. And here I've already put this graph and set this up so that it'll actually get this data. So if you click on those, it'll show you which data that it's using. And I've already labeled it as log y instead of just y, and log x instead of just x. And what do you notice? This data that has once been curved is now sort of straightened out, right? And so this is one way where transformations can be useful, because now we could use log x and y instead of x and y and put log x and y into our regression calculations and into our correlation calculations, and we should be able to get more traction out of using those tools. All right, so let's move on to example 2. Here it says, create a set of data with this function, y equals ab to the x power, and graph this data set. What kind of transformation should be done to make this data more linear? Well, I'm guessing that because, and so now we could just put in whatever numbers we want for a and b. Now we want to probably just do one variable transform, so like a log transform or a power transform just on one side. So if we go to example 2, it already has a and a times b to the x power. And so we could just put in some numbers like 5.2, right? Just anything you want. And now let's put in our formula. So let's not make the same mistake again. Let's lock it in. So here's a times b to the x power. So here I'm going to lock in b. Oops. And once we have that, I could just drag all this all the way down. All right, so this is very, very, very curved, right? Very, very curved, very steeply curved. So how can we transform this? Well, one option might be to transform y, right? So let me put in log y. And maybe I'll put in just the same thing, log base 10 y. And then just drag that all the way down. And let's see what we get. Here we now get this nice linear looking distribution instead of this very, very curvy, like that's almost like a right angle, right? Like very, very curved distribution. And because we didn't change x stays nice and linear, but here we have a logarithmic axis, logarithmic function here. All right, finally, let's move on to example 3. Not finally, I guess. We have example 4 to do. Example 3, it says, consider this data set. The goal of a statistical model would be to allow accurate prediction of birth rate from a country's GNP. That's gross national product. What kind of model would you choose for this data? So it's often helpful to just sort of look at the data and sort of draw for yourself. What do you think might be a helpful sort of model, right? An ideal theory for what the underlying data come from, right? And so this looks very, curvy to me, and to me that looks sort of like what we saw before, where we did the log-log transformation. That looks sort of like that. What kind of model would you choose? Well, I certainly wouldn't choose a linear one, so I'm not going to use the y equals mx plus b format. It's not quite like a parabola shape, right? But I've seen something like this before. I've actually seen it in exponential functions. I've seen something that looks like that, right? And that's y equals e to the x power, right? So I've seen something like that before. And this seems sort of like that, except maybe sort of flipped around, right? And sort of flipped around on, so the x's are all flipped, right? So I don't want to flip the y. That would be like, folding it down. But I want to sort of fold it along the x, right? So for every positive x, maybe I'll want it to be negative, right? So maybe I want to model it with something sort of like, it doesn't have to be e, but some constant to the negative x power, right? And one way that I would advise you to do this is if you have access to a graphing calculator or Wolfram Alpha, one thing is that you could put these equations in so that you could sort of eyeball it and see if you get roughly this shape. And you could play around with it. Feel free to put in different exponents and constants and try to get something, at least the shape that looks like this. The exact numbers aren't as important. We're really looking for that shape. So I'm going to guess that I need a shape that looks something like this. And if you don't want to put in e, you could just use a, a to the negative x power. So that's what I would guess would be sort of the model that I would choose for this data. All right, so example 4, same data set, but it says, what kind of transformation might you try on this data before fitting this data to a regression line and finding correlation? Well, it seems as though this data corresponds to something like y equals a to the x power. Let's see, I drew x too big. A to the x power, right? And we said maybe negative x to get that sort of curve that looks like that. And when we see something like that, perhaps one thing we might want to do is just change one variable. Right? And so that might be one of the strategies that we use, since this corresponds to that to the basic equation y equals a b to the x power. And whenever you see equations of that kind, you probably just want to change one of your variables. So you probably want to play around and either change g and p or change just birth rate to try and straighten out this data.